Welcome to this explainer. Today, we're going to distill a comprehensive, completely hype-free blueprint for mastering quantum computing. Look, if you're trying to get past all those sci-fi buzzwords and want to actually understand how to go from basic intuition all the way up to real hardware execution, well, you are in exactly the right place. I'm super excited to guide you through this. We're going to use a structured approach that's going to make all these complex ideas finally click into place. Okay, let's dive right in by recognizing a fundamental truth about learning quantum computing. To truly master this subject, you really need a highly structured pedagogical approach. Think about it. Diving straight into pure physics is just going to leave you lost in the weeds, right? And jumping straight into coding without the foundational concepts, that is a total recipe for confusion. We really need to strike a balance here. So, here is our roadmap for today's explainer. 1. The quantum learning path. 2. Busting common quantum myths. 3. Layer 1, quantum intuition. 4. Layer 2, algorithms. And 5. The real hardware landscape. All right, let's get into it with Section 1, the quantum learning path. This right here is basically a 3-layer cake, and it mirrors the exact dependency structure of the entire field. You just can't understand the algorithms without the math, and honestly, you can't grasp the math without the core intuition. Following this exact structure is going to save you from the immense frustration of getting lost in linear algebra before you even know what a qubit is. And what's fascinating is that this is exactly how industry leaders structure their own learning paths. IBM starts with bits and entanglement before they scale up. Google's Circ moves from basic circuits to their quantum engine. And Penny Lane builds foundational circuit literacy before throwing you into differentiable workflows.
Moving right along to Section 2, busting common quantum myths.
Okay, you hear this one all the time in pop science. A qubit is like a magical light switch that's somehow both off and on at once. Absolutely false. Instead, you need to think of it as a normalized state whose amplitudes interfere. When you actually measure it, nature forces a classical outcome, a 0 or a 1. But it's the probabilities tied to those amplitudes that are doing the real heavy lifting behind the scenes. Getting this concept right from day one is totally crucial to prevent magical thinking later on. And that brilliantly brings us to another massive myth. People hear about Shor's algorithm breaking RSA, the standard encryption that keeps the internet secure, and they immediately assume quantum computers are just going to instantly solve every hard math problem in the universe. Simply not true. Shor's algorithm is incredibly powerful, no doubt, but it efficiently solves very specific things: integer factoring and discrete logarithms. Factoring actually appears to lie outside of NP-complete problems, which are essentially the hardest class of computational problems out there. We absolutely have to keep our complexity theory rigorous here. Finally, before we leave the myth-busting phase, we gotta talk about hardware claims. You might naturally think all quantum computers are exactly the same under the hood, but D-Wave uses a distinct optimization modality called quantum annealing. This is fundamentally different from the universal gate model systems, the ones that use textbook circuits and algorithms, like the systems built by IBM, Google, or IonQ. We have to make sure we're comparing apples to apples. All right, Section 3, Layer 1, Quantum Intuition. Let's define the qubit properly. Seriously, don't think of a spinning coin. Think of it geometrically. Picture a tiny arrow pointing anywhere on the surface of a sphere, what we call a Bloch sphere. This visualization is incredibly helpful because it directly connects an abstract mathematical state to a concrete geometric picture. It lets us actually see what happens to a single qubit state when we apply quantum operations to it. Next up is superposition. The true power here isn't just about exploring all possible answers in parallel to somehow get them all for free. Not at all. It's all about manipulating relative phase. Just like ripples in a pond, these amplitudes can interfere with each other before you measure them. Quantum algorithm designers use this relative phase to literally orchestrate interference, cleverly canceling out the wrong answers and reinforcing the right ones. Then we have entanglement, which is arguably the first truly quantum resource. Because, if a single qubit can interfere with itself, why do we even need multiple qubits? Well, because entanglement creates a system that cannot be reduced to just the sum of its parts. Think of it like 2 magic dice. No matter how far apart you roll them, they always land on matching numbers. This is perfectly demonstrated by Bell states, where neither individual qubit has a definite value on its own, but when measured together, they show perfect correlation. It's wild. Now, seeing those perfect correlations, you might be asking yourself, does this mean we can use superluminal or faster-than-light signaling? The answer is a very firm no.
Even with mind-bending protocols like quantum teleportation, where a state is transferred between entangled particles, you still require 2 bits of standard classical communication to complete the correction on the other end. So no breaking the laws of relativity today, folks. Let's level up. Section 4, Layer 2, Algorithms. Here's the thing about quantum algorithm design. It isn't magic. It actually relies on a small set of reusable foundational ideas, like phase kickback and amplitude amplification. When you apply these tools, you get algorithms like Grover's, which gives us this massive quadratic speedup for unstructured search, or Shor's, which offers polynomial time factoring. And then we have near-term friendly algorithms like VQE and QoAO. Don't worry about memorizing the acronyms, just know they use a hybrid approach. They pair a quantum circuit with a standard classical computer to tackle complex chemistry and optimization problems. Okay, I have to explicitly hammer this home one more time, just to keep our expectations totally grounded. Shor's algorithm extracts hidden periodic structure. It's the whole reason public key systems like RSA are uniquely threatened by quantum computers. But it is not a magic wand for arbitrary NP-complete problems, like the traveling salesperson problem. And before we can run these massive algorithms, we face a pretty harsh physical reality. Quantum hardware is noisy. Because algorithms require deep, complex circuits, physical qubits easily lose their information. So, to fix this, we build logical qubits. This basically means spreading one single piece of quantum information across many physical qubits using error correction codes, like the surface code. And this is exactly what we are seeing in groundbreaking hardware right now, like Google's recent Willow processor, which actually reported error correction operating below the necessary threshold. Which perfectly sets up Section 5, the real hardware landscape. Take a look at this heterogeneous ecosystem as of mid-2026. If you were only judging these by raw qubit counts, you were being deeply misled. Notice how IBM and Google use superconducting gate model chips, which prioritize error rates and speed, while IonQ uses trapped ions that offer incredible all-to-all connectivity. Meanwhile, D-Wave boasts over 4,400 qubits. But remember our myth-busting from earlier. That's a specialized annealing system, not a universal gate model processor. You have to compare modality, connectivity, and quality, not just the sheer scale. So, to actually run your circuits on these distinct platforms, you need software development kits, or SDKs. These map your abstract math onto their specific hardware workflows. Qiskit is absolutely phenomenal for broad education and hitting IBM hardware. Cirq brings you right up close to the hardware constraints for Google's quantum engine. PennyLane really shines if you're doing differentiable machine learning or VQE chemistry workflows. And Amazon Bracket, that gives you cross-provider execution, so you can write your code once and run it on multiple different systems, from IonQ all the way to Rigetti. And there you have it. We've moved from the initial intuition of interfering amplitudes through the reusable building blocks of algorithms, all the way to mapping circuits on real-world heterogeneous hardware. So, armed with this hype-free understanding of what quantum computing can and cannot genuinely do, the only question left to answer is, what problem are you going to tackle first? Thanks so much for joining me on this explainer, and I'll see you next time.